All right, so when we were talking about derivative connections earlier this year, remember how we have the connections between f of x and f prime, and then we have the connections between f prime and f double prime that actually happen to be the same between f of x and f prime, and then we have the connections between f of x and f double prime. We're going to bring those back, okay? But now, instead of dealing with derivatives, we're going to be using position, velocity, and acceleration in terms of our vocabulary or our terminology that we use. So just as a refresher, okay, before we were using f of x, f prime of x, f double prime. But now we can write what those functions are related to. So an original function, at least in terms of particle motion, is related to its position, okay, its location. The derivative would be velocity. And then the second derivative of position is acceleration. Now there's one thing we kind of have to discuss about velocity. What if I had a velocity of negative 55 miles per hour? We're not used to really seeing negatives in terms of our velocity. Can you think about what this negative is telling us? Yeah?
Would that be like the direction?
Direction. Okay, so velocity is technically a vector. Maybe you've heard that word before, maybe you haven't. Velocity is telling you direction and speed. It tells you two things. So the number itself is the speed, and then the sign is telling you the direction. So if it's negative, depending on which way our particle is moving, like if our particle is only moving left or right, the negative would mean it's moving left. If it's moving up and down, the negative would mean it's moving down. So it's moving in a negative direction. So velocity actually tells us two things, speed and direction. So keeping that in mind, let's see if we can relate these characteristics that we've talked about before, but at least to velocity and position. So when you see the word velocity, I want you to think first derivative, and when you see position, I want you to think original function. Okay, we're going to come back to these characteristics. What if our derivative is 0 or undefined? Can we think about what that tells us in terms of our original function, and then maybe relate that to the position of a particle? If your velocity is 0, if your speed and direction is 0, you're still. Okay, so the particle is not moving. What if your velocity is positive? You're going for, or in a positive direction, okay? So moving in positive direction, okay? So depending on if we're going left or right or up or down, we're moving in the positive way, either right or up. What if the velocity is negative? Going negative, okay? Moving in negative direction. What if we change positive to negative? We're switching. Okay, specifically from moving positive to moving negative. And then what if the velocity changes negative to positive? We're switching again, just in the other way. Yep, switching direction. Are we doing okay so far? Okay. Okay, let's try some other ones, or other characteristics. We're going to relate acceleration, aka a second derivative, to velocity, meaning first derivative. So if the second derivative is 0 or undefined, how is our first derivative, or what's our first derivative connection? If you are not accelerating, constant speed. Okay, so particle is not accelerating. That could mean constant speed. Or constant velocity, we'll say. What if our acceleration is positive? Can you think what's happening to your velocity? It's increasing. Didn't we say essentially if a slope is positive, the function's increasing? Okay, it's coming back to those characteristics. Very similarly, if the acceleration is negative, velocity is decreasing. If acceleration changes positive to negative, velocity changes how? If we change positive to negative, velocity changes into decreasing. There you go. All right, and then the last one would be kind of the opposite, decreasing to increasing. All right, so I'm hoping this isn't going to be too terrible of a connection for us because we're already familiar with the relationships between all the derivatives and the original function. Now we're just relating it back to some type of scenario or terminology where we have position, acceleration, and velocity. So let's see graphically if we can kind of make sense of this example of a particle motion. So the graph below represents the position, okay, the location of an object moving along the x-axis. So that means we're either moving left or right. And I don't think it would be a terrible idea for us to kind of jot down what the different properties of this graph represents. So if I look at a particular point on this graph, what does it represent? If I want to look at the slope of the graph, what does it represent? And then if I want to look at the concavity of this graph, what does it represent? Okay, can we kind of identify those three different characteristics, what it might mean in terms of this particle motion? If I pick this point A, what does that point tell me? Position, because this is the graph of position, so a point will tell you position. What if I want to look at the slope at that point? Velocity, okay, the rate of change of position, the derivative of position. What if I want to look at the concavity or the curvature at that point? That's going to be acceleration, okay? So looking at our derivatives, okay, it starts with position as original. If you take a derivative, you'll have velocity. If you take another derivative, aka concavity, you'll have the second derivative of acceleration. So let's keep that in mind as we check these out. At which points is the velocity equal to 0? So based off of what we said here, if we want a velocity of 0, that means we want a slope of 0. Can we find those spots? What do you think, Christian?
B and D.
Because it says justify your answer. Now, here's where we kind of have to be careful because this is the graph of position. Okay, they're saying it's S of t. So our justification should be something about S of t. Because S of t, what's special about this point and this point? Okay, because S of t has a slope of 0. What's also special about B and D? Maxes or mins? right? Either one of those would be fine. Okay, justifications. At which points does the acceleration equal 0? Okay, so acceleration, we mentioned that would be a character or related to the characteristic of concavity for this graph. So where's the concavity 0? AKA no curvature. I think it's just C. Just C. Okay. AC. You're going for the ACE. ACE. Why C? Because S of t. What's special about this point? Is a point of inflection. Has a point of inflection. Okay, notice how if you trace the graph before that, it's concave down, and then after that is concave up. All right, on which intervals is the velocity positive? We said velocity represented the slope of this graph. We're looking for intervals now, too. What do you think, Christian?
Beginning of the graph to B.
Okay.
And D to the end of the graph.
D to the end of the graph. Okay.
Is that the end of the graph?
Yeah, they have arrows. We'll say negative infinity and positive infinity. All right. So those intervals, because S of t, what? Because S of t's slope is positive. What else could you say? Because S of t is increasing. Okay, either one of those. They're perfect. All right, on which intervals is the particle's velocity negative? Good, Christian?
B to D.
Because?
Because the graph is decreasing.
S of t is decreasing. Or you could say slope is negative. That's fine too. On which intervals is the particle's acceleration positive? Okay, our little jotted note over here, acceleration is related to the concavity of this graph. Where's acceleration positive? Why here? That's good. That's part of it.
It's not one of the ones where it's topping off, like negative infinity to B. That's decreasing slowly.
Right.
Slowly.
Okay, we're going to include this little section in here too. Okay, from C to D. What's special about the concavity from C all the way to the rest of the graph? Yeah?
It is upward.
It's concave up, aka positive acceleration. Okay, because S of t is concave up. All right, and for the last one, acceleration negative, that'd be negative infinity to C because S of t is concave down. Okay, so I highly suggest, at least this is what I do to kind of help me out with these. As soon as I have a graph, I jot down what different characteristics might mean. So as soon as they tell me what this graph represents, I write down what the slope would be, what the concavity would be. Even if we might not need to use it, I still write it, just in case I do. So I think it would be beneficial for us to maybe get in the habit of that. I know some of you that have taken physics are kind of at this level for it to be second nature, but that's completely okay. All right, so this is just something that I use to help me out with the different characteristics and the relationships. Okay, so I'm hoping that wasn't too bad. There are some kind of iffy things, though, when it comes to particle motion that are a little different than the characteristics and the relationships that we've discussed previously. So that's why I want to kind of jot down these 5 important things in terms of particle motion. And they're all kind of similar, but I just want to keep them separate and organized. So if velocity is positive, and if velocity is negative. These two we've kind of already briefly mentioned before. It's the other three that we might have to discuss more in depth, but I think we're okay with these two. If velocity is positive, what can we say about the motion of the particle? How is it moving? Where is it moving? Anything like that. In a positive direction. Okay, if velocity is positive, we'll say particle moving in positive direction. Okay, very similarly, if velocity is negative, particle moving in negative direction. Now, we know velocity actually tells us two things about a particle's movement. It tells us its speed, but it also tells us its direction. So if we look at the sign of velocity, that's telling us direction, but maybe we can focus a little bit more on the second aspect of speed. So what if we want to try to figure out where speed is increasing versus where speed is decreasing? And there's actually a very common misconception when it comes to these two kind of topics here. What do you think should be happening if your speed is increasing? Can we relate it to position, velocity, acceleration, any of those three kind of key things with particle motion? Concave up, so that means acceleration is positive, okay? If you accelerate positively, does that mean speed is increasing?
Yeah.
It could, okay? In our real world scenario, it could mean that. Because we don't really deal with negative directions. We're always used to driving positively. Like when you look at your speedometer, it's always a positive number, right? So you're always moving in a positive direction. But when it comes to particle motion and we have a beginning point, okay, it matters if we're moving left or to the right of that beginning spot. So we have to be careful with the sign. Okay, is it positive or is it negative? Let me ask you this. Pretend for a moment that you're running at a constant speed. Okay, maybe we'll say we're running to the right at a constant speed. In order for your speed to increase, can you visualize or kind of feel yourself pushing yourself forward to move faster? Have you done that?
Yes.
Yes? Okay. So if your velocity is to the right, because you have that constant speed, in order for you to move faster, you'd also have to accelerate to the right. You push yourself forward, right? So if speed is increasing, velocity and acceleration, I'm going to write them in terms of function notation. Velocity and acceleration have the same sign. The direction in which you're moving has to be the same as the direction for acceleration. Because I can easily change this. If you're running to the left and you want to speed up, wouldn't you have to accelerate to the left as well? Okay, so velocity and acceleration have to have the same sign. They have to be going in the same direction in order for your speed to increase. What if you want your speed to decrease? What if you're running to the right? How do you have to pull yourself to slow yourself down? Yeah.
Won't it be opposite sign?
It would be opposite. So can you visualize this, or maybe you've experienced it? When you are running at a constant speed, don't you start to pull yourself back to slow yourself down? Like, don't you start to stand upright a little bit more? Have you ever felt that? You're kind of pulling yourself backwards. So if you're moving to the right, to slow yourself down, you'd have to kind of accelerate to the left. You'd have to change the way your velocity is oriented. Instead of moving to the right, you're going to move it to the left. So in this case, v of t and a of t have different signs. So this is where the misconception happens. If I tell you you're decelerating, meaning your acceleration is negative, do you have enough information to conclude if your speed is decreasing? If you're decelerating, I know in the real world, if you're decelerating, you're slowing down because we assume we're always moving in a positive direction. Okay, our speed's always positive on our speedometer, right? But if you say you're decelerating, that doesn't always mean you're slowing down. Because if we know acceleration is negative, we also need the information for velocity. Which direction are we actually moving? Because if we're decelerating, that means acceleration is negative. If velocity is also negative, we're actually speeding up. Can you see that misconception? If you say you're decelerating, it kind of goes against our intuitive nature, okay, with our driving examples. But if you're decelerating, that doesn't always mean you're slowing down. Okay, kind of tricky. The third thing, or the last one, is if velocity is 0, but acceleration is not 0. Can we think about what happens there? If you have a 0 speed, but you are accelerating.
So you're telling me you're staying still, like you're not going anywhere, but you're somehow accelerating.
Right. So velocity, notice, velocity is the rate of change of position. So your position is not changing, right? Your position is not changing, but your speed is. A treadmill is a good example. Your position is not changing, right? You're on the treadmill forever, right? But aren't you accelerating? Isn't your speed changing? Assuming you're not running at a constant rate?
It's an ignorant question.
It's an ignorant. Not 0. So in terms of a particle motion, okay, think about a particle. If it's on a treadmill, right, it's not moving, but it's accelerating. So what's happening to the particle?
Moving.
It's you got to be careful on how you describe it's moving. It's not moving in terms of position. How can you stay stationary but move?
Burning calories.
In terms of a particle or our hot air balloon.
Up and down.
Yeah? You're changing direction. If you're stationary but you're not moving. Okay? Or if you're stationary but you're moving. So I'm standing here but I'm moving. You see how I'm probably changing direction? I'm changing where I'm locating, right? My position's not changing, so I have 0 velocity. But if I'm rotating, if you will, I'm changing a direction. So if velocity is 0, but acceleration is not, the particle is changing direction. Okay, it's rotating somehow. I know we don't rotate on a treadmill, but that's another good example. How your position is stationary, but yet you're still moving. Okay? Now that we have those 5 down, we'll do more with those tomorrow in terms of like some free response and AP type questions. But at least we have kind of the basics. So particle motion, we have 3 specific functions. We have position, velocity, and acceleration. And just like anything else we've been working with this year, they are derivatives of each other, which means they have connections and relationships between increasing, decreasing, concavity, all that jazz. Okay? We'll do more tomorrow.